1, 2, 3. Okay. But of course, a late start. But you know what? Better late than never, right? Alright, well, pardon me while I get things ready for today's session. Okay, test. 1, 2, 3. Hello, hello, hello. Oh! Hey there! Good seeing you, Trent. Sorry I'm late as always to my own show. But you know what? Maybe that's part of the charm, right? Alright, well, I hope you don't mind, but today is actually going to be quite math-focused and less practical life-focused, in that I'll be covering exponents. So, there's that. And I'll also be scrambling just a bit, too. Wait, logs? Yeah, logarithmic functions? Oh man, I wasn't prepared for that. But yes, they are related. I forgot. Yeah, so exponents are basically kind of the algebra baby version of it, and then logarithmic functions is where you kind of like drag it and then you solve for, yeah. Okay, nice. You know what? I'll take that as a request then. Yeah, okay, you know what? That actually works out nicely. If I do exponents this week, then next week I could try to kind of go over that sort of thing. Because basically... Oh wait, hold on. I gotta fix some stuff. Sorry about that. Open this right here. Okay, I'm still a little bit unprepared. Well, my apologies, but basically, you know, exponents are, there's the number right up here. And then logarithmic functions basically kind of drag them down so they can kind of solve it. And then it's like this something something, and then you can solve for whatever is going on here. That's very rough. That's a very poor explanation, but I think next week I'll definitely do that much better. But today's gonna be on exponents, and if you'll give me just a few minutes, I still need to do a few quick things to kind of finish getting ready. Where is it? Also, I need to give proper credit where credit's due. Of course, you know, there's some things that I can kind of pick up from a book and kind of just ramble on. But other times I like to get inspiration from other sources. And for this week, I will provide the link for that source of why I'm doing exponents at all. That there. Put this here. Okay. Boom. Okay, there's one little piece. Again, sorry for the delays. What else am I missing? Oh, I gotta post this in the chat. There we go. Just in case anyone wants to come by and kind of talk more about that sort of thing. Bam. Yeah, there we go. Alright, and then now I gotta get screen grabs. Now I've done this before with other math YouTubers and their content, so I like to try to give proper credit where credit's due. Now to put this a little into context, even though I try to think of myself as a VTutor, I do recognize that I'm actually not the only one. I'm just the one that's around currently. What I mean by that is that I actually was trying to find out and reach out to other VTutors, online tutors, stuff like that, and I came across this really, really cool dude. Oh, if I could find it. It should be under my watch history. Yes, here it is. This fella called Malev the Diabolic Vtutor, and he does a very, very good job on explaining the material in a very good format. And I say good because it's good for YouTube in that it is long, it's lecture, he provides a lot of solid examples. Fantastic stuff, really. And I'm going to try to get a screenshot for that. Copy. This guy. So basically I'll be kind of condensing his lesson plan because although he explains it very, very well, and I think it's very detailed, and he provides a lot of examples, it is a 3-hour video. And for what the material is, to kind of cover it comprehensively, I think that is fine. For something that's just kind of like a rough kind of coverage and trying to apply it elsewhere, and just kind of more talk about it, and kind of go over the weirdness of the subject matter, then that's kind of what I'm adding my flavor to it. So I will say that I was definitely inspired by his lessons, and I will be drawing some points from it, but I'm not perfectly copying and pasting everything there. It's going to be much dumber than that. He does it quite well. Oh, let me move my head. And of course, you know, at the end of this, there will be a VOD available, and I would like to give due credit to this wonderful guy. Hopefully he'll check it out, but unfortunately he hasn't been around since like 2023. And that's the kind of thing that I counter with a lot of VTutors, is that, you know, they're pretty cool, they're gung-ho, and they have a lot of knowledge, and then they all started around like 3 to 4 years ago. So I guess I'm just kind of the new blood on the block, and just trying to catch up. But thankfully, you know, I have their material to reference from. Now, first of all, what is an exponent, right? And this might come as a little baby explanation, but that's totally fine because that's where we all start, right? If you think about something like math, and specifically addition. Addition is where you have something that's added together, and visually they just combine into one larger whole, right? And then multiplication is where you have a value, a number, and then it multiplies with another number, and then it increases by that many-fold. So instead of just having, let's see, if these are each 2, well, actually, 2 plus 2 and 2 times 2, that's a very bad example. Let me try some other numbers. Let's try 3. There we go. No. Yeah, here we go. Alright. So if these are each 1, and then 1, 2, 3. Again, very, very kind of poor, very rudimentary examples. But I like to provide a visual with when I explain things because I find that is another way in which it helps. A lot of math lectures, they're very kind of numbers-based and follow the formula, and that does make sense and it does work. However, when it comes to kind of getting the greater concept, of what these things actually are and how they look like, I find it to be helpful, especially with exponents, because they're a little weird. So with multiplication, instead of just adding, with multiplication, it's not just adding that number, it is that number that many times, right? So instead of just 2 plus 3, it is 2. If I could just grab it. 1, 2, 3 times. And so with addition, it kind of adds slower. If you use the same numbers but you change the symbol, it gets a little slower than what you would think, right? So 2 plus 3 would be something like 5. 2 times 3 would be something like 6. Now exponents is kind of the next step of that, but much more kind of condensed. So instead of 2 times 3, oh, well, actually that still kind of does the same thing. Let me think. Yeah, let's just keep it. Let's do 2 to the power of 3, right? 2 to the power of 3 is an exponent, which is to say that it's not exactly 2 times 3 specifically. It's not these numbers like this. Instead, it is 2 times 2 times 2. And so what that does is not only is it just a different notation and a different way of doing math, it is to say that instead of there being I have a good idea. Okay. With addition, you're just combining the numbers, right? With multiplication, it is this adding that many times. So you're adding 2 3 times. That's a way you could think of multiplication. You're just adding that number times, and that becomes the multiplier. With exponents, you're multiplying that many times. So instead of just being, 2 plus 2 plus 2 3 times, it is... Oh, let's see if I can copy this. 2 which then becomes 4, which then becomes 8. Yeah, I think 2 to the power of 3 is increases faster. All right. A bit of a weird explanation. Let's see, how can I better visualize this? I don't know if I can. Because what's happening is first, instead of just adding 2 3 times, you have 2 to start with. And you say, okay, now we're going to get... Oh wait, 2, 4, 6, 8. I did that too many times. You're going to have 2 to start with. And then from there, you times it by 2. Cool. But then, instead of just that one part, where maybe with multiplication, you just do another 2 on top of it, which is why I say it's more like adding, because it's just 2, 2, 2. It is you get the whole sum of the previous part, and then it becomes 8. The best way I can think of it is like a fat caterpillar, right? First you have the 2 times 2, that becomes 4. And it's just this bigger monster, and then it is this thing that then becomes multiplied again to become twice as fat. There we go. So addition is, again, is the foundation of it. Multiplication is adding that number any number of times. And then exponents is where it just keeps multiplying onto the previous number, which gets larger and larger and larger exponentially. And displayed on a graph, right? If you have something like an XYZ plane, addition would kind of look something like, how would it look like? You'd have 2 here, and then on top of that you have another 2, and on top of that you have another 2. They kind of look like stairs, right? And then with something like multiplication, it would actually look fairly similar. Because here you're adding... Oh, actually, no. That's incorrect. Caught myself. For here you have the baseline 2, and then you're adding 3. So it goes up a little higher. So it only goes 2 steps, right? Because you're adding only 2 digits. With multiplication, it is that many number of steps that you're adding together. So here you have 2, which is a smaller step than something that would be like 3. But then because you're doing it 3 times, there we go. Then you're increasing by that much, right? Yes, yes, I like this. I like this example. Alright. Now with exponents, it gets crazy. Because again, like a hungry caterpillar, you start with 2. But then you multiply it 2 times. So instead of 2, it becomes 4. And then you get the whole sum of this part. And then you multiply by 2, so then it just goes like this. Bam. In 3 steps. And it also affects the kind of curvature for these things, where maybe addition can kind of just go step by step. Multiplication, well, actually not even that, right? Addition is just kind of like a straight line. Multiplication is kind of like another straight line, but it kind of goes further. And then exponents is kind of where it starts to curve and goes up to infinity. Okay, there we go. Oh, I was worried about this. How would I visualize this thing? Now, that's just kind of what exponents do. So when you break them apart, that's how they look like, where it's just the number multiplied over and over and over. Now, of course, because this is algebra level math, we're going to be using variables, so I'm going to be switching over from using the x symbol to multiply to the dot. The reason why they use a dot is because no number or variable kind of looks like a dot, so it's just accepted as a dot, because otherwise they start doing this kind of funky looking x as a variable, which is just like a bucket to hold a number, but it looks a lot like multiply. So because of that, that's why people stop using the x to multiply. Okay. Now another weird thing is that... Ooh. Oh, okay, I already covered these parts. Got it. Now similarly, exponents can be grouped up and broken down, right? So say, for example, if you have something like multiplication, where right now we have 2 times 3, but let's try something silly, where it is 4 times... Whoops, I just said I was going to do the dot. 4 times 4 times 4 times 4, right? Here is a series of 4s being multiplied together, and then of course you could kind of do it the brute force way, which is to just multiply each together, which is fine. I mean, that's actual math, that's how you would normally do it. But if you want to switch it into exponent notation, I probably shouldn't have done 4 of these 4s. Let me do 3. Then you would do 4, and because they're being multiplied, you just count 1, 2, 3 to the power of 3. Now this only applies to multiplication and not to other forms of combination, unless it's division, and I'll get to that in a bit. But if it's something like, let's say, 4 times 4 plus 4 times 4, right? That's actually something a little bit different. It's not, you know, this plus sign kind of throws everything off. And then you might have to do something where hopefully there's parentheses, so you kind of combine these two, and then you have 4 squared plus 4 squared, and then add them. Again, it gets a little weird. These things can only squish together when they're all being multiplied in a row. It's very niche, but it's also a great way to clean things up, because when you deal with very large numbers, and very large numbers that get very large very, very, very fast, then exponents become a helpful notation. For example, what if we didn't stop at 2 to the power of 3? What if we went 2 to the power of 8? Ugh. It doesn't seem like that bad, right? Because normally when you think, oh yeah, it's, 8 times 2 is, what is it, 16? And so when you're kind of thinking in terms of, multiplication, it only increases by so much. But I believe 2 to the power of 8 is much bigger than that. Hold on, let me just bust out a calculator. I could probably do some napkin math in my head, but I don't want to be wrong because these can get very big. Yeah, that's what I thought. 256. 256. Alright. Now the reason why those get so crazy is, again, just like the Hungry Caterpillar, they kind of multiply not just the 2, but the whole chunk of the 2's multiplied previously, then it multiplies to this one, and then this whole thing gets multiplied by 2, and that whole thing gets multiplied by 2, and it gets bigger and bigger and bigger. Until you get very large numbers. Now, of course, when working with very large numbers like these, they also want kind of rules and things to simplify these processes. So then that way you can kind of work with them and make them usable. And thankfully there's kind of rules that we could follow. And let me bust those out according to this guy. Again, he is the G. Alright. So the way you could think of exponents... Ooh, I love this example. Is because they're multiplying and because they combine into a little corner, they also kind of make things a little confusing. Like, what if you had 2 to the power of 3 times 2 to the power of 3, right? If you had those two together, then you might think, well, is there a way to make it easier? Yes, there is. Thankfully, because these base values are exactly the same, you can kind of do a weird thing where the exponents themselves add. And it's just the exponents that add, and that becomes 2 to the power of 6. Now, how does that work? On a visual way, I'll just do it. Basically, 2 to the power of 3 is, as drawn up previously, it's basically 2 times 2 times 2, and all that is multiplied by another pair of 2 times 2 times 2. Now, thankfully, we don't have any kind of addition, we don't have any subtraction, we don't have any weird stuff in between. They're all being multiplied together, and because they're all being multiplied together, we can kind of squish up and group them and just kind of count how many 2's there are. So we got 1, 2, 3, 4, 5, 6 2's all being combined. Well, then that would mean it could be written as 2 to the power of 6. Now, of course, because it is still a number being multiplied, there is a solution to it, and I could write it out, but I don't want to because what I'm trying to show is how exponents function, not necessarily just to get a number solution quite yet. And so a way that this could be written as a kind of formula that can be used is if you have a variable like x to the power of a, and it is being multiplied by the same base value, base variable. So we're going to use x again. Let me scoot this actually. Let me scoot it and put it nice and big. Yeah, I like this. These will be our rules. Alright. To the power of b, then that could be rewritten as x to the power of a plus b. And another way that can be written is because if maybe you have like variables in the exponent parts, right? And variables in the exponent parts will come up more with logs. Also, I gotta say, it's kind of funny. Trent is a cool guy, and he's doing tree stuff, and he knows tree stuff, and he's working on logs, logarithmic functions. But like, they're also called logs. I just got that. That's funny. Okay. Sorry. So, for example, if you have something like 2 to the power of 2, and then, yeah, right? Multiplied by 2 to the power of x, right? How does that work? Because now you have a variable in the exponent part. Well, using our rule, we don't even have to really think that hard because the base values are exactly the same. And so this can be actually rewritten as 2 to the power of 2 plus x. It's not multiplied by x, it's added together because it is the total number of 2's that we would have. So here we would have, if we break it apart, this would be 2 times 2, and it is multiplied by an unknown number of 2's, which we will call x. But you're still kind of counting the 2's, so you're counting 1, and then here's 2, and then here's, you don't know, x, I guess, x number of 2's. So you do 1 plus 1, 2, and then plus however many there are. That is why you have the addition on the top. Very cool. Alright, now let me check out this next rule. Ah, here we go. Now, of course, if you're thinking, okay, well, now we can kind of add, you know, exponents, right? Is there a way to subtract exponents? Like, is there a way to get these kind of a little bit messier? And yes, there is. And the way you do that is with kind of the opposite of multiplication, or rather the other half of it, which is division. So here we would have something as a rule. X to the power of a divided by x to the power of b is also known as x to the power of a minus b. So, then we get some kind of weird stuff going on where, and again, it makes sense because let's say, for example, if you have a bunch of, I don't know why I keep using 2's. Let's just do some weird numbers. Let's go with 9. let's go 9 to the power of 7 divided by 9 to the power of 5. Yeah, odd numbers. Alright. So if we write this out and break it into pieces, because again, we know that exponents are basically things being divided, we can kind of stretch this out and it'll just be, let's see, 1, 2, 3, 4, 5, 6, 7. So here we have 7 9's, and here we're going to do 5 more on the bottom, because the bottom is 9 to the power of 5. Yeah. 1, 2, 3, 4, 5. Okay. Again, I know this seems repetitive. I know I'm kind of going over the same thing. However, the reason why is because that way you can have a visual to reference to anyone who watches, but also, in case you ever get confused, you can always brute force this thing. If you ever forget, you can always just stretch out these numbers and try to do your best. I mean, if you have something crazy like 4 to the power of 100, I don't think you should just like draw a bunch of 4's and like scribbling them on the walls like a madman. like don't do that. But you technically can, and if you want to make some really obscure art of like a bunch of 4's and you call it, you know, math homework, then sure, why not? But basically, what I'm doing here is I'm trying to visualize how these things can actually get subtracted from each other. So this kind of draws from another principle in math where 1 is equal to 1. Alright, I know, basic, right? 1 is equal to 1. However, I was trying to think of, well, what other ways are to describe this thing? Well, what about if you have like a big piece of tofu, right? A big piece of tofu is equal to a big piece of tofu. Now, the reason why I bring this up is because what if you start chopping up the tofu, but it's still all squished together, right? What if you cut it in half? Then basically you have 2 halves of tofu, but you have 2 of them. So you got like 1/2 plus 1/2, it's 2 over 2, it still equals 1, right? Even if you cut it again, and then it becomes 4 over 4. You have 4 pieces of tofu. This is how many there are. Or this is how many pieces it's been cut into. Whoops. Cuts. Pieces. And you have 4 total pieces. So 4 over 4 is still equal to 1. You still have the same thing as basically a giant thing of tofu. It doesn't matter how many times you slice it or dice it. It's still all the same. To that end, when you are doing multiplication and division, this applies because you can't really change things if you multiply it by 1, right? So if you have like 100 times 1, it's still 100 because it's just one big piece, right? If you have 100 divided by 1, it's still one big piece, so it's still 100. Similarly, you can also, because this doesn't really change anything, you can kind of add all these weird ones to whatever side of the equation you have, right? And so that's why people do things like they say, well, if I have something like 58, no wait, that's not a 58. 58 over, I don't know, 92. And I really, really don't like the 92 on the bottom. I just don't. Well, I could multiply this whole thing by 1 to simplify it. But that doesn't make sense, right? Why would I do that? Well, because it doesn't change anything. But also, what if I say, well, if I have something that was cut into 92 pieces? Then it'd be 92 over 92. And then I could kind of have this, where I would have 92 multiplied on the top and multiplied on the bottom, but not really, because they also cancel each other out. Because again, it's completely redundant a lot of times, and it just doesn't make sense, right? Because then if you cancel out the 92s, then you still end up with the same equation. So that's why this is allowed. Now, on a more practical level, what if you have a whole bunch of 9s on top of each other and they're all being multiplied? Well, the way this kind of works in this situation is that you can kind of do something called cross-canceling, where you would say, well, I basically have 9 divided by 9, and it's being all multiplied to this stuff, and everything's all kind of squished together. So I could just actually cancel out these 9s with each other. And you can kind of go down the row. And as a visual, then all you have left are 9 times 9. And you can either write it as such, or you could leave it back to where it was, which is 9 squared. And I apologize if it seems like a bit of a jump in logic, but I kind of hope that makes sense. That's why I'm able to cancel out all these 9s. And then that's where we're able to get from 9 to the power 7, divided by 9 to the power 5, is now 9 to the power of 2. But a very, very simple way of kind of doing this without having to draw these numbers, without even have to really thinking about that multiplication rule, is just with this nice quick rule of when you have something to the power of something, you can have it minus each other. Now, of course, now that we're introducing minusing, it gets a little weird, right? Because, like, well, what if you minus a bigger number than what you got? So, say for example, let's flip the script, and let's instead have 7/5. No, wait, that's not how it is. 7 to the power 5. 7/5 is like this. Yeah, no, that's not it. That's not what we're doing. It's a 7 to the power 5 divided by 7 to the power of 9. Now, in this example, they still kind of cancel each other out. Where you just have a whole bunch of 7s, and you have a whole bunch of 7s down here. But, you know, you're going to have more 7s on the bottom than you are going to have on top. And then, unlike previously, where you could just kind of have this invisible 1 on the bottom, or something where it would equal like 9 times 9 over 1, which is basically what happened here, and then it bounced back to here. Now you're kind of left with something where you have is that 4 of them? Yeah, it should be. 1 over 4 7s. Alright. Boy, what a mess. Well, thankfully, you could still squish them because they're all being multiplied on the bottom. So you have 1 over 7/4 to the power 4. But that isn't quite what we're looking for. There's supposed to be a minusing somewhere, right? Where'd that minusing go? Well, it already happened. And in fact, the weird thing about exponents is that when you have a negative exponent, it's basically a fraction where it's on the bottom of it, because you already took too many out. So negative exponents aren't actually some kind of weird dimensional negative multiplication. It's just basically division. You're multiplying, or you're dividing by this large number that's being multiplied repeatedly. Now, of course, this begs the question of what if we go for broke, and what if we try to zero this thing out? How can we mess this up, right? What if we have something where x is to the power of 0, right? What if we perfectly match things together? What would happen? All right, well, let's check it out. And then let's do an easier one, right? Let's do 3 to the power of 3 divided by 3 to the power of 3, right? Because we're going to try to minus these. Drawing it out, it would look something like this. 3 times 3 times 3, 3 times 3 times 3. Well, using the rule before, where, you know, a number over itself is basically equal to 1 when they're being multiplied in a squished container like this, we can kind of cancel them out. They all become 1. And then you get this weird thing where you have 1 times 1 times 1 over 1 times 1 times 1, which is also equal to 1 over 1, which equals just 1. Almost seems like a fluke, right? How did that happen? Well, what if we do something different? What if we do maybe 2 to the power of 1 divided by 2 to the power of 1? And I might not think of it as to the power of 1, but every number that doesn't have a power actually has kind of a hidden power. And I explained this on a previous video, but if you think about, you know, how many x's are there, right? Well, what does x be multiplied by? Well, it doesn't seem like it's being multiplied by anything. It just seems like there's one x, but that's how you count that 1. Because you have something like 3x, that means there are 3 x's being multiplied to each other. But if you have an x standing on its own, then it's technically a 1x. Similarly, just like there's a singular x is the 1x, a number without an exponent is technically just to the power of 1 at all times. So then, even if we try to be cheeky and say, all right, well, what about 2 to the power of 1 divided by 2 to the power of 1? Well, that just equals 2 over 2, which also equals 1. And so, when we do have something where it kind of works out that it's x to the power of 0, that almost always equals 1. Now, thankfully, once again, this very cool guy brought up an edge case where what if, you know, this seems like a principle that would apply to all variables. But what if it's something weird like 0 to the power of 0? Because what that basically would mean is that would look like 0 divided by 0. But you can't have anything divided by 0. Would it still equal 1? And of course, even though it's math, math is not an exact math. So it kind of depends on who your teacher is and what they want as an answer. just ask. And then they'll tell you like, oh yeah, no, it doesn't work. It's a not real. It doesn't function. Or maybe they'll just be like, yeah, whatever. Just make it 1 all the time. So there you go. All right. Now, it might get a little funky because we're looking at addition and subtraction with exponents. So now you might be wondering, well, what if there's multiplication? What if there's division? Yeah, those exist. And the ways those exist is as if you have something like, I'll draw it on top. If x is to the power of a, and it is being not multiplied, but also to the power of b, then that's when you get x is to the power of a times b. All right, now this can get weird, and I'll try to give some good examples and bad examples on how to apply this. Oh my gosh, I only have 10 minutes left. Jeez, okay, I didn't even get to the fun parts. Okay. So here we have, let's say, let's try 10 to the power of 2 to the power of 2. How is that different from something like 10 to the power of 2 times 10 to the power of 2? Wait. Yeah, it's not. Because when you do something to the power of 2, it basically multiplies. Because, again, just like how the principle of the exponent 2 would break this down into 10 times 10, this 2 actually breaks down into the whole part that it is encompassing, which is 10 to the power of 2 times 10 to the power of 2. And so that's kind of what it does, is that instead of just thinking like it's just the immediate number, it is the whole brick inside of it that it multiplies. So even if you have something like a 3 to the power of x, y, to the power of times 8, and then all that's to the power of 2. No, 3, right? If you're going to break this 3 into pieces, because it's still an exponent, it takes the... My head's in the way. It takes the entirety of the insides of this thing and puts it into the... how many times it's being multiplied, which is here is to the power of 3. So we would get something like 3xy times 8, and then this whole thing is multiplied 3 times because it is to the power of 3. It takes the entirety of the thing. Now, as a trick, as a helpful tip, as a shortcut, the way in which you could shorten this notation is what they provide with it, that you can just have those two numbers being multiplied. Which is why something like 10 to the power of 2 to the power of 2 could also be rewritten as 10 to the power of 4, because that is 2 times 2. It gets weird because what if it's not just a nice chunk of the exponent that you have inside that you can work with? Yeah. Say, for example, if it's something like 2 to the power of 2... No, wait. We need a variable. Smiley face to the power of 2 plus 3 all to the power of 2. It doesn't quite distribute into it because if you try to do that, you get 2 wrong things. Oh, hi there! Hey, what's up, Catrius? Thank you for coming by. Today I'm covering exponents and how to do them and how not to do them. I like to do both because it's one thing to explain how to do them properly, but I like to do things wrong, so that way if someone does that in the classroom, then they'll be like, oh, well, that's why it doesn't make sense. Anyways, so yeah, right now I'm just doing some silly math with smiley faces instead of typical variables, because why not? Okay, so looking at here and following our rule, where we have this kind of shortcut where it's a variable to an exponent and set to another exponent, it does not quite work because it is not a clean variable. It's actually an equation that's in the middle here. It's not something like this where it's all just one number to a singular power. So the way that you might do it wrong is if you tried to distribute the 2 into these, right? So that would be, let's see, smiley face, 2 times 2 would be to the power 4, plus 3 to the power of 2. This is the wrong way, and we'll kind of go over the math in that in a bit. But what would the right way be is something like this, where you could rethink of it as smiley face to the power of 2 plus 3 times. I know, right? Smiley face 2 to the power of 3. And it actually splits up like that. So that's how that exponent would actually work. It wouldn't kind of work like that. And we could kind of double check our math because we know that this is correct. And to show that this is wrong, we'll just plug in a number, right? Let's say, I don't know. Let's make it easy. Let's make it 0. If smiley face equals 0, right? Oh, wait, he doesn't have a tongue. Okay. If smiley face equals 0, then we would have 0 to the power of 2, 0 to the power of 2. These are just zeros. And then we have 0. Oh, wait, no, that actually works out, doesn't it? Darn, I have to do an actual number. Hold on. Yeah, no, I think 0 actually does work nicely. Let's try 2. Yeah. Okay, let's try 2. Okay. So then we would say, okay, this now equals 2 to the power of 2, which is also known as 4. Let's do that nice and easy. 4 plus 3 is, what was that, like 7? And so then this bubble is 7, this other bubble is 7, and then you get the answer of 49, right? Because when in doubt, if things look a little too fishy and you're not too sure, just plug in a number for the variable and see if it works. So that's how it's supposed to be, right? But if you accidentally distributed the exponent into the inner parts, and you still have the smiley face equaling 2, then you have 2 to the power of 4 plus 3 to the power of 2. Well, 3 to the power of 2 is, what, 9? Yeah. Alright, and then you got 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. And then, what is that, like 25? Sure. Alright, so now what happened is that by doing it incorrectly, you have the answer 29 or 25 when you should have had something like 49. So that's why whenever you have kind of addition or something within the brick of exponents, if there's any kind of plus symbol and a variable, you kind of just want to leave it alone and don't touch it. It's like poison. Just leave it. A lot of these exponent tips and tricks only work if it is the entire thing that has this variable or this exponent. So what could have worked is if this was slightly rewritten, right? What if it was smiley face to the power of 2 plus 3, and this whole thing was to the power of 2, and then that whole thing was to the power of 2. Now, if this whole thing, this whole chunk right here, is you don't touch it, and you just think of it as one kind of big variable or big number or big set that's kind of by itself and it's to the power of 2, then these can actually multiply nicely. You can kind of shorten it to smiley face to the power of 2 plus 3 and all that to the power of 4. Oh, okay. So that explains that rule for a bit. By the way, Catris, if you have any questions about math stuff, please let me know. I am an actual tutor, so I have conferencing software here, so if you ever want to come on live and talk about and share screenshots of some of your homework, I can actually do that. That's kind of my shtick. But for today, I'm kind of covering exponents as a planned lesson, and then next week I'm gonna be helping Trent here with logarithmic functions. I'll try to do well. I don't know if I will, but we'll see. If it's a mess, it'll be a fun mess. And then also, just to kind of give credit where credit's due, this is the guy that I looked up and was trying to connect with, but he hasn't been VTubing for a while. The Diabolic Vtutor. This guy is legit. He actually has these YouTube videos that kind of went way into depth about the subject matter. Very digestible, very easy to understand. What I'm doing is kind of a more kind of tailored experience and also a very dumb experience. Oh, I shouldn't say that. A silly experience. Yeah, I like that. Okay, let's see. So now, I think I kind of went over negative exponents, but I didn't create a thing for it. Yeah, okay. So if you're going to be multiplying variables together, those exponents add, and then, okay, no, I do have this as a negative minus exponents. Ah, okay. Now, a way in which this could have been solved a bit differently is if instead of having addition here in the middle, is if it was multiplication. So I'm gonna jump way over here, and let's try something else. Or you know what? Let me put the rule first and try to explain it backwards. Here we have x to the a, y to the b, all y to the power b, all to the power of c, and that's because they're all being multiplied, would be x to the AC and y to the BC. Nice. Hold on, do I really want to... Yeah, I should cover that. Okay, so going back to this example, with the smiley face and the 3. What if they weren't added? What if they're being multiplied, right? Then what I could have is something like smiley face to the power of 2 times 3 to the power of 1. And then that is all multiplied by 2. Cool. In this example, now that there's no addition, now that things are being multiplied, then I can kind of split this into both. Wherein it would be, let's see, smiley face 2 times 2 times 3 to the power of 1 times 2. Okay. Now, that might be a little weird, because also, beforehand, and again, the fun thing about this kind of level of algebra is that there's a lot of like weird ways you can kind of like mix and match to get to the same solution. So here we could even have, let's say, if we have smiley... Well, actually, no, you can't do it. Oh, yeah, you can, I think. Smiley face to the power 2, I think you just have like 3, because you're already multiplying by 3. And then this whole thing is now to the power of 2. And this is to say that because these are being squished together, because now you don't have that word separation, it's still basically the same thing. It's just a different rewrite of it, where they're now together as a thing. Wow, I'm explaining very poorly. That's fine. Because the principle is the same. And that you wouldn't just apply to the exponent multiplier just to the smiley face. Because as you split it apart, again, another way to rewrite this is 3 smiley face to the power of 2 times 3 smiley face to the power of 2. And because they're all being multiplied, they can all kind of squish. And because they both have the same variables, it kind of works out very nicely. So then you just have 3 times 3, which then becomes 9. And then you have smiley face to the power of 2 multiplied by with another version of itself, then it becomes 4. And then this is basically a rewrite of the same thing, of where you could just kind of split it nice and easily, where you have smiley face 4 times 3 to the 2. It's all a bit of very circular logic. But the key is that you don't have to split them up like this. You can if you want that kind of visual, but just by following the rule of exponents, it becomes a little bit easier to manage. Okay. I think... Oh, here's a simple one. Well, I mean, I already covered this. But basically, if you have a variable with a negative exponent, that's also known as it just kind of being flipped on its head. like so. And I think I covered that a bit earlier with, where was it? Right over here, yeah. And that's way, because division is like where you, instead of adding exponents together to kind of shorten it, you kind of minus them. And so them being flipped upside down on the bottom part of the division line, is where you kind of get weird things like negative exponents. And is that kind of the gist of it? Yes and no. There's some other rules that this guy presented, which makes sense, but I'm gonna hold off on those for now because, well, I mean, I'll just put them on here, right? Again, I would recommend, of course, checking out the Diabolical Vtutor on his lesson on covering this because it's much more comprehensive and it really covers examples that are more proper. As well as some that are improper and shows you how they don't work, which is what I really like. Let's see, if x to the power of a equals x to the power of b, then a equals b. Generally, yes. But the weird thing is if it's a to the power of x equals b to the power of x, then a kinda equals b, but not really. And the reason why is because the first one works is because it kind of makes sense. It's kind of a self-contained explanation where if you have, let's say, I don't know, if 2 to the power of 4 equals 2 to the power of question mark. Well, what is the question mark? It's like, well, it's probably 4. And you'd be right. Right? But here on the flip side, where instead of the matching exponents, where the bases are the same here, and the exponents are different, here you have the bases are different, where you have, let's say, something to the power of 2, does 2 to the power of 2, and x to the power of 2. What is x? X could be 2, but because it's an even exponent, it could also be negative 2. And it's just kind of the weird thing that kind of happens with math sometimes, where because we're not using things like absolute values in this notation right now, it's kind of flexible where x can either equal 2 or negative 2. Because if you have 2 times 2, then yes, it matches, right? Everything lines up. But because when you have something to an even power, then those negatives, they cancel out. So then it kind of becomes like this mess where you would have 2 answers. I don't think this would normally come up in a classroom setting unless your teacher's really cheeky and they want to see if anyone gets it for extra points. So there might be that. Okay. I am way past time, but that's totally fine because I started late, so I'll keep going for just 1 more minute. Now, the reason why I wanted to cover exponents is, again, to not only just regurgitate what he said as a numbers thing, but also to present it as a visual thing. Whereas, and again, this is kind of what I wanted to cover, is that with addition, it's more just like adding blocks together. With multiplication, it's where you're adding still, but just this number of times. But with exponents, it gets larger by multiplying to the previous chunk. And so it gets much larger, much bigger, much faster. So instead of doing 2, 2, and 2 to be 6, you have 2 times 2, which is 4, and then it is that entire 4 that is multiplied and then grows to become 8. And so the shape of those things kind of increase much more dramatically, whereas maybe addition is just like a few, steps up, and multiplication, if you graph it out, it becomes kind of like a line. With exponents, they kind of become this weird parabolic figure that kind of goes into infinity and beyond. Now, not only that, though, the funny thing is the same thing works with negative exponents, too. So say, for example, if you have 2 to the negative 3, right? remember what that is basically 1 over 2 to the 3. And so then you're going from maybe that's something that looks like, 1/2 to 1/4 to 1/8. So graphing that out, you're kind of going from 1/2 here to then 1/4 of that to then 1/8. And it just kind of swings downward like that. Whoops, not quite upwards. But where it almost goes, and if you keep getting larger and larger negative exponents to something, it gets very, 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 very close to touching 0, but it doesn't quite touch 0. Yeah. Alright, there it is. So, to all that came by, I wanted to thank you so much for coming by to my stream. As always, I'm kind of open to tutoring. A lot of this is more kind of just covering these kind of lesson plans and ideas that, have been covered countless times, but what I like to try to do is to give personalized tutoring to when someone needs help with more specific math questions or a specific problem, stuff like that they have. And so I hope to do that next week with logarithmic functions. And Trent, if you have any specific problems, just feel free to send them my way, or you could even join. Like seriously, this is conferencing software. It's anonymous too, so you could do like a voice call, and you could screen grab. But yeah, it's whatever you or anyone that you guys want. I'm here to tutor pro bono. I think that means free, right? Pretty sure. All right. Anyways, thank you all for coming so much. Always appreciate it, and I hope you all have a good night. And I'll see you next week. Until then, have a good one. Aw, yeah.